far we are still in the area of two-dimensional case. So let's have some brief review. Okay. Now, our original problem is about the connectivity equations like this. And for this problem, you can define the Dirichlet, right? Okay. Now, and what we did in the past is we reduced this into a Schrodinger equation. Okay, Schrodinger equation is like this. And for the Schrodinger equation, assuming that the zero is not an eigenvalue, then you can also define the Dirichlet mass and Q. Now the reduction from here to here, you still remember how to reduce from this equation to that equation?
Make substitution for Q with the
You put what?
Laplace and F.
Amazing. Some R, right?
Yeah.
So Q equals what? Laplace square root R divided by square root R. Right? Okay. And okay, so we keep this in mind. Okay. Now, once I redo this, then you can see that when you know the Dirichlet map lambda R, then this will allow us to know the Dirichlet map of Q, right? Now, when we do this reduction from here to here, we also talk about what we call the boundary determination. You remember? The boundary determination. That means the Dirichlet map here, this one actually determine, like at least you have to know two things, two boundary values. That's the R, the restriction of the conductivity on the boundary, and also the gradient, the first derivative restricted on boundary. I mean, even though I don't know how to determine from the Dirichlet map to the conductivity contribute, but at least I'll be able to know the boundary values of these. Actually, you can determine more depending on how what is the regularity of R. In this case, you can see that we're assuming R is at least twice differentiable, right? At least twice differentiable. And then what will be, so once this is reduced to the Schrodinger equation, then what will be our main tools to solve this English problem? What do we do? I mean, if you think about Schrodinger equation here, okay, what do we do in order to investigate this English problems? What is the main step we make? We have
the equality of integrals.
Special solutions, what we call the exponentially growing solution. That means the E x k dxc, okay, equal to E x c dot x, then 1 plus omega or W x c, right? And this solution carries one of the key property. That means in a property law, omega xc is less or equal to a constant divided by c. Satisfy this key estimate. And you can see that as dimension is greater than or equal to 3. That's enough. All we need. I mean, this solution itself is can be used to prove the uniqueness. Okay. But only in the dimension equal to 2, then we know that the problem is formally determined. That this solution itself cannot be just used directly to determine the potential Q. You have to use some other, right? But in any case, this solution is our main tool, the main things. Okay. So here, last time in the previous 2 lectures, we talked about 2-dimensional case, and in the 2-dimensional case, and these solutions in angle 2. So solution sometimes just like xk equal to c dot x. I mean, it depends on k. And because c is choosing to be k, can choose to 1/2 k, the components plus the k. So choosing a k is a vector, two-dimensional vector. Then from here, I can construct a c. So then you can look the spatial solution looks like this, depends on k. Well, of course, I can also choose the other one with minus sign here. You have another spatial solution, right? And combined together, you can do something with the uniqueness problems. Now here, before we move on, so I want to make two notes, two remarks here. Okay, so here, remark 1. Okay, remark 1 is that you can see R has to be, so in this approach, okay, here we'll talk about this approach, okay, R has to be at least C2. Or sometimes you can think about weak set is W to infinity. W to infinity, that means the function is twice differentiable, the derivative is infinite. But normally, for simplicity, you can C2. But actually, when we prove the local uniqueness, you can see that it has to be C3. Because the potential has to be C1, so it's C3. But the approach cell, from the approach you can see that it's require at least the C3, because otherwise you cannot make such a reduction, right? You can see more one. And the remark 2, actually we didn't fully use the structure behind K. Now, what does it mean? This means here is so the remark 1 is obvious. The remark 2 is hidden. Why? You think about these space solutions. Okay. Now this spatial solution depends on K, right? Okay. K. Now what is the K? K is a vector, which has to be within some certain given value. So this K depends on the size of the potential, the C1 norm of the potential. But anyway, for as long as the small k is greater than that, the solution can be constructed. So you can see that you have a mini spatial solution, which depends on k. Okay, so a lot of structure behind this. So this solution is important because this solution contains information regarding the potential. So our goal is actually trying to get that information from this spatial solution. Of course, it goes through a complicated way, right? But the things we are trying to point it out is that when we try to extract solution, the information of Q from the solution, we didn't pay too much. We didn't pay full attention to this K. Okay, that means there's a family of solutions, lots of solutions, but however, we didn't carefully use the dependence on K. Now, what we did is through in the existing approach, basically we are doing some integration. In K. That's all we did. That's what we did when we construct the operator, right? Which operator we take the kind of Fourier transform. I mean, something like the Fourier transform. Then transform back. The way you transform back, you're doing actually the integration in K. that's the place we use the K. So, but however, you can see if you use just integration in K, so somehow you are not use the information locally, you just average the entire values, right? So it's not a good way to get all the information of the potential from the experimental solution. But however, we don't know how to use other approach in order to get more information from the experimental solution, besides the integrations. Okay. And the reason is because that there's restriction out here. Okay. The restriction here. And also there's some other technical difficulties. For instance, now what exactly mean by you have a better way to understand this space? That means you have to think about this is a function of K. For instance, you freeze the X variable. Then you think about this is just a function of K. And this function may be differentiable in K. Maybe somehow this function itself depends on some of the differential equations in K variables. Okay, so if you can go to that detail, about the differentiation in K, then the differential identity, differential equation will give you much more information than just the integration K. So that's the things we want to pay more attention in the new approach. Okay. So here we're trying to talk about a new approach. New approach is different from here. The new approach is only for the dimension in 2. Okay, it does not go through this reduction. It goes through another reduction. And actually, there's a two. Here in this part, we can only talk about the one new approach. Okay, it will reduce Q, reduce this from C2 to C1. Okay, gamma here obviously has at least C2, right? But we can have another different approach so that only require gamma the R to be C1. And there is a new approach. Probably a couple of years ago, more than 10 years ago, and they only require C0. It's another new substitution reduction. But here we can only talk about this one, reduce the C2 to C1. All right. So actually, last time we have already began this. So here this involves a lot of computation. So I'm going to go through some elementary computation that maybe help you to understand some of the structure. But when we go to some stage, we have to skip some things. And just only talk about the idea. Okay.
So Dr. Sun,
Yes.
with this for N2, if I remember, you said they only did it, they proved it global uniqueness then instead of.
And so far, we only get the local uniqueness, the generic local uniqueness. But the new approach will give you the global uniqueness. But new approach, the global uniqueness is not for the Schrodinger equation, it's for the continuity equation. Because it does not pass through the Schrodinger equation. Yeah. Okay. Okay, so here, let's see. So you have an original equation, right? So you have an equation, connectivity equations, okay? So suppose you have so we're going to reduce this to the first order system, okay? So here is what we're going to do. So let's say that now from this equation, suppose you have a solution, U is a solution. Okay, solution meaning is a classical solution, the C2 functions. And then you can actually compute the BU and D bar U, right? Okay, so once this is a C2, so these two things make sense. Okay. So therefore I'm going to multiply this pair by square root of R. Okay, I'm going to call this the BW. So here you can the notation is that's the D operator, D bar operator. Okay, then you can see that our original derivative dx is equals to D plus D bar bar divided by 2. Make sure the notation, I follow the same notation. Then dy is equal to d bar minus 2 pi. Okay, so here I'll fix notation. Okay. So here I'm going to do the transformation like this. So this transformation allows us to show that this equation is equivalent to the first order system. So this system is like that, d bar. So I'm writing the matrix form. Okay, dw. Then minus 0 q, q bar. 0 dw. Okay, so q is equals to -1/2 and d bar r. Okay, so that's the system, first order system. Of course, this is first order complex system. Now, this system is not a big deal because this system, you see that it's actually it's a complex system, right? Actually, these two components, the system has two equations, right? These two equations are related. I mean, they are not independent. They just write the system this way for convenience when we are continuing to do it. Okay. So you can see that. So this system is equivalent to what? So this thing is equivalent to. Now here the equivalence is unclear, but the system, if you write it out, it's not a big complicated system equation. It's just means d bar b is equals to qw, and dw is equal to q bar v. Okay, so this is the system. Okay. So the first step, we're trying to prove that these two things are equivalent. So from here, you're going to get this. Okay, and vice versa. So once this is done, then you can reduce the Gibbs to Newman map for something related to system called, you can see it's called a Cauchy set. Okay. So first, we're going to work out the computation field. We're only, so you can see this thing is equivalent to two things, right? So I'm going to just work out this one. The same I'm going to work out this. That's again. Okay? So first we're going to begin with the this equation. So this equation from here, if you take the gradient of that, you can get plus e plus the gradient gamma gradient u. So, right? Then from here, so here we're in this direction. Okay? It goes to this direction. Okay. So from here you can get that so you divide the r to the side. So plus u plus the plus log gamma log r gradient u. Okay. Right. And then I'll just replace these derivatives of differentiation using the d and d bar. Okay, so this equation, so this means that so I'm going to call, so for the convenience, I'm going to call this coefficient I'm going to call sigma is log r for the convenience. Okay? So then I'm going to write this differential equation like this. So d bar du. So that's give you Laplace. Okay? Then plus, and so here's gradient. So gradient has two components. Okay? So this means that the d bar plus d applied to the applied to sigma. Sorry. So this is the x derivative applied to sigma, okay? and then times the x derivative, the x derivative to the u, so that takes exactly the same form. Okay. Then you have the second part is the y derivative. So the y derivative will be sigma minus sigma minus 2i, then times the u minus the u. So here I'm just using the d bar to replace the dx dy. Right? And then you can see there's a algebraic computation you can do. So from here, that's with d bar du plus here, so when you multiply, so you have 1/4. So I'll put 1/4 outside. Okay, put 1/4 outside. Then you have so sometimes you involve d bar. I'll put d bar and d bar together. So d bar sigma, d bar u, and sometimes for something you don't have bar. So d sigma du. Then plus some middle term like d bar sigma du plus d sigma d bar u. So you multiply this couple out, you'll get that. And then the other term, you do the same thing. The other thing is involved 1/4. Then you have I squared equal minus 1, so minus 1/4. And then you have the similar term, d bar sigma d bar u. Then here, without bar, you have minus become plus. So d sigma u, then the middle term will involve the negative sign. So therefore you have minus d bar sigma u minus d sigma d bar u. This is the same. Okay. Now we observe that you have some cancellation here. Because of the minus sign, you can see all the term here, 2 bar and without bar are all cancelled. It's cancelled. And the mixed term remain the same. Here minus sign, minus, plus. Okay, so you have 1/4, and then you have another 1/4, total is 1 time, right? So this is d bar du plus 1/2 d bar sigma du plus d sigma d bar u. Okay? Okay, so this is a important middle step. Okay, we reached here. Now you can see this equation. Well, it's not that complicated, right? Really, it's not. But what I'm trying to point it out is that this equation, from this computation, you can see that once I made such a substitution, okay, once made substitution, from here, you can see this equivalent. The equivalent. You can from here, you go back to here because you're adding all this term and the reverse process you can go. So here, there's no, it's exactly equivalent, okay? Okay, and then from here, from this equation, we're trying to get this equation, one piece, okay? Then if I use another way to compute, here, if I change replace the d and d bar like this, then it can locate the other way. Okay, so here, from here, so here, when I go from here, I don't care the order. But now we pay attention to this order. Okay? So from this equation, I'm going to multiply square root r. And also I'm going to put back what is the sigma here. So multiply by the square root r. Okay? And you have this. And you have the square root r, then d Now what is sigma? Sigma is log R. Okay? Then du. Then plus the d sigma, or then you have log squared R, then you have d sigma, then d bar u.
D log R, right? For the sigma. The second sigma.
Second sigma,
No, next to the square root of R in the last term, sum.
okay, here,
Yeah.
Yeah, you said we're putting log back. You put sigma.
d sigma, yeah. Yeah, of course, I do. Log R, okay? Then d bar u. Okay. Okay, now here we have to be more specifically here. Now what is the this? Now how do you differentiate that? They follow the same differentiation rule, so this is the d bar r over r, right? Okay, so this is equal to this. And then you have a square root r here. The square root r here, this cancels with this becomes square root r. Okay, then you have so suppose I multiply 1/2 inside. So you have 1/2 here, then you have 1/2 here, right? Okay, and then you can see what exactly is this. This is equal to d bar square root of r. Right?
Yeah.
Okay. So